If the integrand of an integral is a combination of only trigonometric functions, we say that it is a trigonometric integral. To evaluate trigonometric integrals, we have two major tools. The first one is integration techniques. For example, integration by substitution or integration by parts. But in addition to that, we have trigonometric identities, so we can really manipulate the integrand in many ways just using trigonometric identities. And as you know, we have many of those. Trigonometric identities are closed in pairs. By this I mean that if you look at the basic trigonometric Pythagorean identity, you will see that sine x and cosine x are one pair, tangent x and secant x another one, and cotangent x and cosecant of x is another one. Why do I say closed pair? It's also true about the derivative and the antiderivative of those functions, that you really stay within a pair. Those pairs are also closed under differentiation and integration. Okay? It is always possible to express any combination of trigonometric function as at least one pair, the sine and the cosine. I would like to recall that we have four trigonometric functions which are actually some quotient and combination of sine and cosine, which is the tangent, the secant, the cotangent, and the cosecant. So is it always possible to take all the trigonometric functions and express them using sine and cosine? We first are going to review some Pythagorean identities in trigonometric functions. The most important one, and you really should remember this, is the sine to the power of 2 theta plus cosine to the power of 2 theta equals 1. Now I can get other ones. For example, if I divide everything by sine to the power of 2, I get this Pythagorean identity, which is actually this 1 plus cotangent to the power of 2 theta equals cosecant to the power of 2 theta. Now I'm going to divide everything by cosine to the power of 2 theta. And now I'm getting another Pythagorean identity. Tangent to the power of 2 theta plus 1 equals secant to the power of 2 theta. But I get much more. From here I get that sine theta is the square root of 1 minus cosine to the power of 2 theta. And also this is true that cosine theta equals the square root of 1 minus sine to the power of 2 theta. So as you can see, I can take an expression with the radical, and if the radical is like 1 minus something to the power of 2, maybe there's a way to get rid of radicals using that. And from here I get that secant theta equals the square root of tangent to the power of 2 theta plus 1, but also the tangent theta equals square root of secant to the power of 2 theta minus 1. To avoid radical, the parity of the exponents of each trigonometric function play a major role in the integration process. It is very, very important to avoid radicals in all cost. So you really need to know, okay, all those identities that are written here very, very well. I would like to recall some derivative and antiderivative of trigonometric functions, also to show you the closures of the pairs. Okay, so we know that and that. Look at the cosine and the sine as a closed pair. We also know that and that, and again the secant and the tangent as a closed pair. Okay, and this one, and again the cosecant and the cotangent as a closed pair. Let's start with the use of substitution trigonometric integrals. First, you want to make sure that the functions are within a pair. It's very, very important. Then you observe the parity of the exponents. Which functions can go into the du, so what left can be expressed as a function of u without radicals. Radicals are very, very difficult, so you don't want to have radicals when you integrate functions. And then you want to try your choice of u. If it doesn't work, change it to be the other function. Why I'm saying the other function? Because we are working within a pair. So after your integrand is a closed pair, then you have only two choices for the u. Is one of those in the pair? Still doesn't work? Maybe you have to use other technique of integration. Let's start with an example of the pair sine and cosine. We have to integrate sine x to the power of 5, this is an odd exponent, times cosine x to the power of 2, which is even exponent, dx. The truth is that most trigonometric integrals are just a sophisticated u substitution. In the u substitution, we looked at the composite function and we took the inner function to be the u. Here we cannot do it because if you look at this, for example, it's a product of two functions and each of them is composite. So the u can be cosine x or it can be sine x. What I should put in the du, so the leftover, will have only even exponents, because I love even exponents. When I have even exponents, I can use the Pythagorean identity to write the sine as cosine or the cosine as the sine without using any radicals. So in this case, I will definitely would like to take the du to be sine x dx. Let's do it in the right way. Du will be negative sine x dx. The only reason to take the minus here, you don't have to, is because I always prefer that u will not have a negative sign in front of it, but it's okay to take du sine x dx and u as negative cosine x. You can also do it that way. So now I'm going to split up those exponents as I want. So instead of sine to the power of 5, I'm going to have sine of x times sine of x to the power of 4. This step is one of the most important steps that you do in trigonometric substitution, is you rewrite, but you rewrite it in a way that you can really take each one of those parts and translate to get an integral of the variable u. So because also I have the minus sine x dx, I also have minus, but then obviously I have to multiply everything by negative 1 to keep it exactly the same as the original integral. So now what I have to do is really to write everything that it's written here as a function of the u. So let's start. So the u is cosine x, so I don't have any problem with the yellow part of cosine x to the power of 2. I also have no problem with the negative sine x dx because this is just a du. But I have a problem with sine x to the power of 4. Well, so I will need to use this Pythagorean identity. So if I will have sine to the power of 4, this is just 1 minus cosine to the power of 2x to the power of 2, but cosine of x is u, so I get that sine x to the 4 is 1 minus u to the power of 2, all of this to the power of 2. So now I'm going to check again that indeed I didn't forget anything. Very common problem is that ignoring the dx. When you do trigonometric integrals, the dx is a major part of the integral. Okay, now I just have to do some algebra here, okay? So I have to take 1 minus u to the power of 2 to the power of 2, and then I'm going to multiply by u to the power of 2, okay? And I just get a polynomial of u. So I can go ahead and find the antiderivative now. And the only thing left to do is to take care and substitute cosine x instead of u. And I get that. Well, to understand better, we will try to repeat with the wrong choice of du and u. It's very important really to experiment in those integrals. It's okay to do mistakes in technique of integration in general, but you have to learn from each one of your mistakes. So now on purpose, I'm going to pick the wrong u and the wrong du. But also if you noticed what I did here, I first choose the du and then the u. Usually in a regular u substitution, I choose the u and then I choose the du. So now I'm doing something which is bad. Let's say that I made a mistake and I decided to take du equals cosine x dx. So du is sine x. Now let's see what the problem is. Okay, I don't have any problem with the yellow part because this is just going to be u to the power of 5. And cosine x dx is just the u. But what about cosine x? Well, I get that this is radical of 1 minus u to the power of 2, which is a big no, no, no. We don't want to have radicals. Okay, so I want to recall again. In the one that we did before, everything works because we didn't have radicals. We just have a very simple polynomial of u after all those substitutions. Because when you have a pair, you have only two choices of du and u, then it's not a biggie if you made a mistake and you just pick the wrong one, because you will pick it up in a second and you will change your mind and just take the other one. Let's now do real workout about what is the general case of integrating sine to the power of mx times cosine n x dx. As we already understood, everything is just about the parity of m and n. So let's see. If m is odd, then it's always a good idea to take the du to be negative sine x dx, because the leftover of the exponents of the sine x is now going to be even, which is always a good idea, because I can express this always as a function of the cosine, because also if this is the du, then the u is cosine x. And this is exactly the Pythagorean identity that I'm using. What happens now if n is odd? Then we do exactly the same, because n is odd and I don't like to have odd exponents here. I'm going to take the du to be cosine x dx. Now, the parity of the exponent of the cosine x is even, so I can express it as a function of the sine x or the u. And here I have this one. If one of those are odd, then we are all set. And I really don't care about the other one. If both of them are odd, then there are two ways to do the integration. We can take u to be cosine x, or u can be also sine of x. The more problematic one is when both of them are even. Then we are not going to do that, but we are going to use the reduction formulas or half angle formula. But now when we do integration, we really call it reduction formulas because they are reducing the exponent. And we have obviously two of those. Cosine to the power of 2 theta is 1 plus cosine 2 theta over 2. And the other reduction is that sine to the power of 2 theta is 1 minus cosine 2 theta over 2. We are going to do an example that will use the reduction formula. The exponents at both of them are even. Now I'm going to do a lot of trigonometric identities, and then you will see that the integration part is going to be pretty easy. So I have to reduce both of those. So I have that. Let's write it down. Okay. The theta is x. So when you do that, you're actually doubling the angle. So now you have cosine 2x. Okay, so now we have to multiply everything out. Okay, but this is easy because this is like a minus b times a plus b. So it's the first one to the power of 2, we get 1. And the second one to the power of 2, so we get cosine to the power of 2 of 2x. So now I need another reduction. But pay attention. Every time when I do reduction, I double the angle. So now I'm going to get double time of 2x. So I'm going to get now 4x. Okay, now I get something kind of a linear expression of cosine. And when I get a linear expression of cosine, I'm all set because now I know how to integrate everything here. So let's do the integration. Okay, I'm just simplifying a little bit the algebra first. And I get something really pretty easy. The most confusing part here is all those 1 over 4, 1 over 2. So just take your time, make sure the algebra is perfect, and here the algebra is perfect. Okay, so I can continue and I can just take the antiderivative. So the antiderivative of 1 is just x, and the antiderivative of cosine 4x using a u substitution. I didn't show it here, but you have to use a u substitution. Okay, when u equals 4x, and you get that the second one is sine of 4x over 4. Again, I would like to recall, you can just differentiate it and check to see if this is right or wrong, and it is right.